Yes, I will, but I don't get time. I have all the lectures recorded. So I will start uploading. I keep forgetting. I have just one lecture could not be recorded. I think that's the first greedy algorithm lecture, but rest.
Ma'am,
Yes.
sorry, you had told me to remind you about that solution of the
Yeah, I
recurrence
have to do
relation.
it on paper, or I'll just see something which is
Okay,
uh,
fine. Sure.
self-explanatory. I'll send it to you, but just give me this
Okay.
weekend. I have not been able to give you assignments also, although I have prepared the assignments, but I just had to edit a bit. Okay,
Okay,
so
fine.
this time there is the only your 10 marks is for assignment. You will have a midterm. I think you have seen the notification. So there'll be a midterm online, but I'll give you some sheets to practice, which you can do so that you get an idea about how the are going to be in the exam. Okay, I will try recording lectures probably in the evening when the laptop is free at night. I'll just put them on upload. Okay. Uh, okay, I think everybody is there almost. Okay, so today's uh, problem is one more greedy algo that we are going to discuss. It is known as the. Are you able to see the lecture? This is lecture number 14. So I'm just using a PDF existing one that I had. I'll be emailing or uploading this as well. So we are going to have a greedy algo for the problem of codes and compressions. So what are codes? You know, all your alphabets, numbers that we represent on your system all have their ASCII values, and we represent them uh, in normally in 8-bit codes for all the characters. So that is the norm. Normally, you'll say this 8-bit code reserved for a character. But sometimes, when we wish to store a file, the frequency of the characters is different. So, if we are giving 8 bits for a character whose frequency is, let's say, only 5 out of 2000, then you are wasting a lot of space giving it that much space for storage. So, what we are trying to achieve here in the coding problem, or we can say the compression problem, we want to analyze what kind of data we have by looking at their frequencies. So if some character is very frequent, we assign it a code that takes less space. So normally what happens, you have a binary code, each character has a binary string associated with it. And what we are when you say you have to compress the file, what you are trying to do is you're trying to reduce its size. And how would you reduce the size? You want to use as many lesser bits as possible. So how do we reduce the size of the bits to store a character? We assign them codes, different codes which are of smaller size. Okay, so we use as few bits as possible to represent a character, and then we code according to that code. And then when you have to, normally you compress a file, then you have to decompress the file. The code has to be unique so that when you compress, you're able to decompress and get the correct result. So for that, we look at the frequency of the alphabets, and based on the frequency, you decide what kind of code you should be giving to these alphabets, and then you code your or compress your file using that new code. Now, normally what we have a fixed length code. Like we say, for normally you'll say there's 8 bits assigned for a character, all the characters are going to be 8-bit. So that's a fixed length code. But when you are trying to compress, you cannot go with the fixed length code, because then compression doesn't mean anything. You are again going to use 8 bits for each character, so nothing, you cannot reduce the size. So what we go for is a variable length code. So we give code words of different lengths to different alphabets, and obviously when you compress using these codes, you have to decompress using the same reference. So if I am coding in some language, to decipher, the other person should know that language to get back the original text or data, whatever you are sending across. Okay, so if you look here, there's a table. Okay, for example, we have these six alphabets. This is the frequency. So the frequency is the number of times a character repeats. Just let it be 45, 13, 12. These numbers only. Okay, if we have a fixed length code, let these be the only characters in your file. And here in this row you have a fixed length code. All of the alphabets are represented by 3 bits. Okay, so 0, 1, 2, 3, 4, and 5. So you have fixed length code. So obviously, if there are if you add up the frequencies, you will get whatever number you get. You have to multiply it with 3 to know how many bits are being used. Okay, so the fixed length code here requires 3 lakh bits to store the file. You actually have these numbers in thousands. The frequency is in thousands. Just a second. Okay, so if you use fixed length code, you will use 3 lakh bits to store this data. Now, if you want to use the variable length code, for example, this is the variable length code that we have given. This is our problem is to find the best variable length code for a given frequency of characters in a file so that we can compress it to the best possible. So if you're using variable length code, this is the number of bits you will use. Okay, 2,24,000. So there's a mistake here. The first one is 45 into 1. So 2,24,000 bits. So you are saving around 80,000 bits, so which is a lot of space. So if you have a bigger file, the compression obviously will give you more savings in terms of the number of bits. So, okay, let's go here. Now, anything that you have to code, like I said, when you code using a particular scheme, then you have to decode with the same scheme. So, for example, here you see they're given two different coding schemes, C1 and C2. In C1, A is 0, 0, and C2, A is 1. So it's just slightly different. C is same and D is this. So there are two different schemes that they're using. Then if you encode the word bad, bad is B, B is 0, 1, A is 0, 0, and D is 1, 1. So this is according to scheme C1. According to scheme C2, B, A, and D. This is your code, coded file or coded text that you want to encode. Now, when you have to decode, you have to obviously use the same. If something has been encoded with C1, it has to be decoded using C1. Obviously, you cannot decode it using C2. So, a message has to be uniquely decoded with reference to a particular code. Okay, so so that it is decoded in only one way. So for example, you use some other code to decode it, then you might, maybe you get a sensible message out of that, but it is not going to be the original message. So this is just an example of how you can uniquely decode. But if you look at C3 here, the way C3 is designed, or the way the coding is done in C3, this is the third scheme. If you B, A, and D. Okay, this is the code you will get. But when you are trying to decode, either you take this 110 string as one character, you could also be possibly doing replacing it with, because A is 1, it could be A, and then 0. It kind of gives you a wrong, but it's not like you don't see a unique pattern to decipher it. So if you see here, just let me clear this. So 110 and 1111, it can be either decoded as bad or ACAD. Okay, so if your codes are not designed in a particular way, in a specific way, then you might land up with something like this, where when you are trying to do the inverse, you are not getting the right answer, or you're getting multiple answers and you have to select one from that. That's why we say when you are using variable length codes, okay, for fixed length, you have to take 3 bits at a time, and those 3 bits are assigned to a particular character. So it will not create any ambiguity that this might be some other character. Every character has a 3-bit code. But if you see here, if you look at A and B in C3, there is an ambiguity. B can be written as AA0. Okay, and in fact B can be written as if you take this one as A and 10 as C, B can be written as AC. That's why bad can be written as ACAD. So there it is not clear. Why? Because the other codes, the codes for some alphabets, they are either prefixed to some other alphabet, or here in this case they are a suffix of the particular alphabet. So you can possibly use this or use BAD as the inverse when you apply the code C3. So that should not happen, because this will, obviously it is not a, it will create ambiguity. So this has to be avoided. So for that, what they do is they define something known as a prefix code. So fixed, like I said, fixed length codes are always, you can uniquely decipher them. Okay, because every alphabet or character has a unique code allocated to it. In case of variable length codes, if the code for one alphabet is a prefix or suffix to another alphabet code, it will create ambiguity. Okay. So what they define, to remove this ambiguity, they make a standard. They call something as a prefix code. So a prefix code is a prefix free code, actually, where none of the codes of any character will be a prefix to the code of another character, which removes this ambiguity that was created here. Because B, in case of C3, your B was 110, A was a prefix to B. Okay, so the ambiguity should not be there. This is not a prefix code. So if you look at C2, C2 0, is there any zero, any code who which starts with 0? None of them starts with 0. So A is not a prefix of any of the codes. 110, B is not a prefix to any other code. Suppose C was 1100, then B was a prefix. So C is just 10, it is not a prefix. What is a prefix? Prefix is something at the beginning. So no character can be represented as another character and some other alphabet. For example, in the C3, B could be represented as A10. So that should not happen. None of the code should be a prefix to the code of another alphabet. Okay, so that is your prefix code definition. Okay, this, the example here in front of you, this is a prefix code, because none of the alphabets, they the code of none of the alphabets is a prefix to the code of any of the other alphabets or characters. Okay, so when you use a prefix code, or you can say a prefix free code, to decipher a language, you can do the inverse in only one way. So there is no two ways. So how does it help you? Because whenever you find the first code word, whenever you find the code matching a particular character, you know it is that particular character. There is no other character that starts with the same code and extends with some other digits. Okay, so we can just remove that character, or we can say this is the character, and start reading the rest of the string of characters to decipher it. Okay, so what we are trying to do here, our problem first, what we are doing here is first defining what the problem is. We are interested in finding a prefix code so that we can compress to the best possible limit. So there is a limit of compression. I give you a, let's say, 500 KB file. It's not that you'll reduce it to 1 KB. It will go down, let's say 300, 350. So we are getting some ratio of compression. What we want to do is we want to get the best possible compression for a particular size based on the frequency of characters appearing in the file. Okay. Now, go here straight away. So, for example, we have four characters A, B, C, D, and the frequencies are given, and the fixed length codes are given here. So, this is my frequency, this is my fixed length code. So, how do you calculate the number of bits? Every frequency is to be multiplied with 2. So, if the character appears 60 times, it is stored using 2 bits. So, you're using 120 bits, then 5 into 2, then 30 into 2, then 50 into 2. This is your fixed length code. And when we are doing variable length code, that is your prefix code here, we are storing A using 1 bit, we are storing B using 3 bits, we are storing C using 2 bits, and we are storing, okay. So this will be your total. So if you see here, the first one will give you 200 bits. So 120 plus 10 plus 60 is 170. No, sorry. It's not 50. Last one is 5. So this gives you 200 bits. So this is only 5. So you get 60 and, okay, so this is 200 first one, and the second one is 150. So you're getting a 25% saving by changing the code from fixed length to, okay. So, okay, let's not go over the remark. So whenever you have an alphabet and you have its frequency distribution, then the number of bits used is frequency into the number of bits used for storing that alphabet. So now coming to the problem, we are trying to find a solution to get the best compression technique for a particular file where we are provided with the frequency of the characters that are present. Okay, so it is a greedy algo. We'll see what the greedy part is, where we want to produce a minimum cost or an optimum prefix code. What would be minimum cost? Minimum cost would be the best compression method, that compression size that you would get. The, you can say the best compression saving. So, Aman, can you check somebody's mic is on? Okay, done. Okay, so we are trying to get the maximum savings. We want to get maximum savings by using the developing a prefix code for a particular problem so that we get the maximum savings and we have a minimum cost. Cost would mean obviously when you save more space, you are reducing the cost. Cost would be in terms of space that you are using. Okay. So how do we develop this prefix code? So it's important then we actually want to develop a variable length code because fixed length code does not give you that option of compression. Compression can be done only when you have a variable length code. In variable length, our greedy approach is that the character which appears most frequently, we try to store it using the least possible number of bits. And that obviously reduces our usage of bits. The character which appears least frequently, I can give it more number of bits because I know it's going to appear very few times, so it's okay. But if I give most number of bits to the character whose frequency is the highest, then I am wasting space. So the greed is allocating the least number of bits to the character with the most frequency. So that is the concept of greed in case of Huffman algo. Let's go to the steps first. So how do we proceed? What we do is we take two letters from the list of alphabets given that have the smallest frequencies. Okay, and we create a tree, subtree, not a tree, a subtree that has these two characters as leaves. Okay, this is a greedy idea. We why are we picking up the characters with the smallest frequencies and creating them as a subtree? Because we want to do something like this. We are trying to use we are trying to create a tree like structure where the path to a particular leaf node where the path to a particular leaf node gives us the code. Okay, we create a tree so that when we travel from the root to a leaf node, this leaf node is A, so the code of A is going to be 000, like it's mentioned here. When we go from 001, we reach the leaf node B, so the code for B is 001. Again 010, we reach C, 011, it's D, and 1 is E. If you see in the problem, this E45 is the frequency of E. E is the most frequently appearing character, and what we want to do is we want to keep it up in the tree, closer to the root, so that the number of bits assigned to it or the code assigned to it is the shortest. The least frequency ones, we start building the tree in a bottom up fashion. So we first take the alphabets with the least frequency and we make it a subtree and we grow the tree. So we made this subtree and then we make another, we take, you'll see in this in a while how it goes. So these are again less frequency compared to this. Then we join them together. Then we join them with the one with the least frequency. So we'll do the example that will clear it up. So your code will be determined by the path you take from the root to the. So your first step is picking up the alphabets with the least frequency, two of them, because you want to create a tree. You join them using a root node, okay? And the frequency of the root node will be the sum of the frequencies of the two. So the if x and y were the ones with the least frequency, okay, the sum of the frequencies is fz. So we are this is what we are doing. We are actually creating a tree, and the frequency of x plus frequency of y is frequency of this node, that is the parent of these two nodes. So the actual characters will appear only in the leaf nodes, they will not appear in the internal nodes of the tree, because we want to find the code. To find the code, we'll go from root to every leaf, and that path will determine the code. And we will uh, okay, so we will assign the we will assign the code 0 to the left side and 1 to the right side. This is how we are building a subtree. So after that, what we will do, We will take off x and y from our main set A, which is the set of alphabets of uh, the characters that are there in the original problem, and we will add z. We are doing union z. So we take out these two, we add the subtree back, and your subtree means z, which means frequency of z is added. So next time when you're checking for the least frequency of two uh, characters, you will check it along with the frequency of z. We'll just come to that in a while. And the number of, how many nodes did we take out? We took out x and y, but we added z back. So overall, we reduced the size of the set by one only. Okay. So slowly we are kind of uh, shrinking the set. You'll see that with an example. So we'll do the same procedure till we are left with only one symbol. And whatever tree is created as a result is going to be your Huffman, will give you the Huffman code. If you remember when we created expression trees, what would we do? We would take A and B, and whenever we found an operator, uh, we would apply it on the operands, and then we would push the subtree back into the stack. So you were taking out two uh, operands from the stack, and you were pushing back one, the subtree, which would serve as the operand for the next operation. So it's similar to that. So let's do this problem. Okay, let me, okay, let's do it here. Then I'll do another problem. So this is my set. There are 5 characters. Every character slash is the frequency of the character. So your first step for Huffman code is to select the characters with the least frequency, which is C and B. It could be C and D. It doesn't matter. Whatever order, 15 and 5 are the characters with the least frequency. So what you do is we create a tree. Let's make it here. This is B. This is C. What was the frequency of B? 15, and for C it was 5. So the overall sum of the frequencies is 20. So I'm taking out these two and I'm pushing in, let's say, X with the frequency of 20 as the new character in this set. Okay. Now, my next step is to take out again the same procedure. I pick up the two characters with the least frequency. So what are the two characters? It is X and D, because the, or it can be A and D, whichever you want to choose. Okay. If we choose A and D, we will get another subtree like this, and the frequency of A and D together will be 35. Okay. If we choose X and D or X or A, we will get a different tree, but the codes will be different, but they will be unique and they'll be prefix codes. Okay. So let's go by what is done here. Then the next problem we'll do on whiteboard. So you take C and D first and you create a new node here, N1 with the frequency of 20, rest is the same. Now you have 4 characters in your set. Now the next two minimum, what they have chosen here, they've chosen A and B like we did. You could have chosen anything, N1 and B or N1 and A. So we chose A and B, it will not matter. So when you join them, this frequency is 35 and you have two subtrees and the final node E. Now, what is the out of this set now? You have the frequencies 35, 20, and 45. So the minimum is 35 and 20. You will merge those two. So when you merge 35 and 20, you get 55 and 45. So now you have a subtree and E with a frequency of 45. When you merge those two, you get a frequency of 100, and this is your final tree. So whatever tree you are creating, you have to, we assign 0 to the left and 1 to the right subtree. This is the value, you're giving the path a value 0 if you're traversing to the left and a value right. So what will happen? This is what kind of eliminates the prefix problem. It is we have to generate a prefix free code. So how do you travel from your route to A? You travel with a path which is 0 0 0. Okay. And how do you travel to B? 0 0 1. So if you see, A is not a prefix of B, because to reach B you're taking a separate path in the opposite direction. 0 and 0 are same, the first two characters are same, but the entire character is code is not a prefix of the other code. So for C again, 0 1 0. For D, 0 1 1. And for E it is only 1. So the most frequent character has the least size codes. For all others, in this case, you have a 3-bit code. Okay. It all depends on how the algo works and how the frequencies are, how they get merged. You could have had only this much of the tree. So there could be some element here with a code of 0 1, but that's not the case here because the way frequencies are distributed. So this is the code that is obtained using Huffman coding. This is the optimum minimum cost prefix code for this distribution, for this frequency distribution. So frequency distribution will affect the way, the kind of code you will generate at the end using this algo. Okay. Uh, okay. This is the algo for this. So what you're doing, you have a set of characters with frequencies allocated to them. You put all of those in a priority queue, and then what is your first step? You take out two elements from the priority queue, min elements. So you extract two and you'll club them together, make a new node whose frequency is sum of the frequencies of the two nodes you just took out, and insert that back in the queue, and then repeat the whole process. So once you're done with that, you repeat the whole process. So there's a question written here. Why do you have the loop running from 1 to n minus 1 and not n? Because when you are left with one node, you're not supposed to extract that. That is the actual final tree that that gives you the Huffman code. So once you return this, you will extract the last element left once you're done with this for loop. Okay, so this for loop runs with, how many times does this for loop run? N minus 1. And technically, this 1, 2, there are two extract mins. That means two times the tree will be readjusted, and then you are inserting back the answer. So again, once you insert something, your tree is adjusted. It's a heap, min heap. So according to this code, this is 3 log n. Okay, so you can say 3n log n minus 3 log n. So this is overall, this is the bigger term. So it is less than or equal to n log n, the runtime. Login tree. What are your basic operations are insertions and deletions in the min heap, and that every insertion deletion takes log n time. And how many times will you do it? At the most, you will do it. If you go back to our problem, how many times did we do it? uh, okay, let's go to the original set. Okay, so we took out, I'll just count it. Okay, we took out, let's say, oh no, this is not the one. Yeah, this is the original set. We took out C and B. So 2, and then we inserted back the answer to that, right? Then we took out, let's say we took out these two, again 2, and we inserted back the sum of the frequencies. So this is that note. For example, then we, let's say, took out these two, again 2, and we inserted it back, and then we took out these two, let's say we inserted that back again. So 12, and you have 5 notes. Your n is 5. There are 5 characters. So it is almost 2 into n, or 2n, yeah, roughly 2 into n. So when we have 2n, we take it as n. So n times you are doing log n adjustments in the heap, so it is n log n. 1, yes. Okay, you don't need to do the theoretical part of this. Okay, I want you to take out your pen and paper. Okay, and I'll give you a problem. We'll do it together. Okay, can you see this? Can you see this screen?
Yes, ma'am.
Okay, so on the left you see characters along with their frequency. So let me. So what is the first step? You find the characters with the least frequency. Okay, so the characters with the least frequency are A and B. So I'll add the frequencies, and the frequency is 14, and I'll name it X. So this is my new node X with a frequency of 14. Okay, this is my first step. Now again, I repeat the same on my set. Now I have X, C, D, E, F. Out of those, this and sorry, not this. 12 and 13 are the lowest frequencies. So I will create another tree, C and D, and I name the root Y, and the frequency is 25. So this becomes Y with the frequency of 25. Okay, now I have 4 nodes: X, Y, E, and F. Okay, now third round, I will pick up what is the least frequency, 14 and 16. So I'm picking up X and E. Okay, and lesser one is X. So I will add E here, and the sum of the frequencies is 30. Let me name it Z. So you can say this and this club together is Z with the frequency of 30. Now you still have, what do you have? You have this Z and F with you. X is already gone. So Z is 30, Y is 25, and F is 45. So you will actually merge Y and Z first. So Y and Z will be merged, and the total frequency will be 55. I name it S. Now you have another node S and 55. So obviously you have to merge it with I have to merge it with F, F here, and the total frequency will be 55 and 45, which is 100. And just name it capital R. This is our root. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. So this is my tree. To get the code of to get the code of to get the code of A, you have to travel from R to A. So you get all zeros. For B, you get 0, 0, 0, 1. For C, you get 0, 1, 0. For D, you get 0, 1, 1. For E, you get 0, 0, 1. And for F, you get 1. So you see the most frequent was F, and for that the code length is least. And the next frequent is E, you have length 3. उसके बाद you have D and C, again length 3. And the least frequent A and B get the longest code. Why? Because they are at the bottom of the tree. You started building the tree from there, and you started merging it with uh, nodes with the next lowest frequency. So the lowest frequency ones get the longest code. So is it clear? You can raise your hands. You want something. This is a very simple mathematical procedure. You just have to understand how you do it, how you get the codes, and what is the greedy solution. The greed part is that you are trying to get the highest frequency character have the lowest length, lowest code, and this is a prefix code, so that none of the codes is a prefix of another code, which eliminates any ambiguity once you are doing the decoding part. Okay, clear? Any questions on this? Okay. So this is pretty much what we will do for our greedy algos for now. Maybe if we have time in the end, we'll try and explore some other problems in all of these. But these are the basic problems that we discuss under the heading greedy algos. So we are still left with our next topic is actually graph algorithms. We have already covered some in our greedy because they were greedy in their approach. And next, we will be moving on to graph algorithms that includes your DFS, BFS in detail, and also uh, something about directed graphs and how to find the shortest path in them. There's something called it as topological sort. There's a Bellman-Ford algorithm. So all of that will fall under your graph algorithms category. So for now, this is pretty much your greedy algo. If you have any questions, you can ask me now, or you can just text me if you have any issues, or email me. All right, Aman, can you take the attendance, please?
Yes, ma'am.
Is it possible to use that encoded information without decoding it? It obviously, when you decode something, you are trying to. Uh, Here, the purpose in case of Huffman coding is to reduce the size. So when you send a reduced size file to somebody, he has to decode it, because otherwise it'll all be garbage. If the original code was using 3 bits, and then I use a prefix code to compress it, or वहाँ जाके when I send it to somebody, it's like writing something, encrypting something. For decrypting, you have to use the same method. You cannot, or it's not the same method, as in the inverse of the algo that you are applying. So I'm applying some algorithm to encrypt my message, send a secret message somewhere. Then that person needs to know what technique I have applied in coding my message. So it's the same thing. When you are encoding, if you just want to store it, even if you want to store it in your own system in a compressed format, when you actually go to view that file, you have to decompress it to get the original one back. Or you have, if you not, as in, you don't have to change it back from prefix code to fixed code and then see it. If you know what the prefix code was, even if you don't know, if you just know the frequencies and you know Huffman coding has been applied, then you get the codes and decipher it back to the original. Okay. Anything else? Attendance taken? Attendance done, Aman? I
Ma'am?
can't hear. हो गई?
Yes, ma'am.
Okay, fine. All right. Thank you. Enjoy your lunch.
Thank you.
Thank you.
Thank you, ma'am.